In this video, I'm going to go over transformations of the absolute value function. We're going to discuss the different effects of transformations on the parent function of the absolute value function family. So this sheet that you see here on the slide, I have this as a resource in Google Classroom. It's titled Transformations Cheat Sheet. You'll want to refer to this. This will help you when we go to describe transformations. So I want to review with you. We saw this a little bit with linear, but I want to go over this again. So f of x equals a. So this a is a transformation. And if we just follow the lines up, it tells us if a is negative, it's a reflection over the x. If the absolute value of a is bigger than 1, then it's a vertical stretch by a factor of a. If the absolute value of a is in between 0 and 1, then it's vertical compression by a factor of a. So that's what a does to your graph. The next transformation is a b value. So what does b do? Well, let's take a look. So if we follow that line down, then we can see that b, if b is negative, it's a reflection over the y-axis. If the absolute value of b is bigger than 1, then it's a horizontal compression by a factor of 1 over b. So notice it's the reciprocal of b. So it's 1 over b there. If the absolute value of b is in between 0 and 1, then it's a horizontal stretch by a factor of 1 over b. So that's what b does to your graph. So this is what b does. So that's what b does to your graph. Now let's look at h. H is inside the absolute value bar. H is the tricky one. H is going to do opposite of what's there. So if I have plus h, it means the graph moves left. If I have minus h, it means the graph moves right. So this is the value to look out for, is the h value, because it does opposite. And the last value is the value outside k. K is going to shift your graph up or down. So if k is positive, then it moves your graph up. If k is negative, then it moves your graph down. So I'm going to leave this on the screen. And I have just an example for us to do. I just want us to identify the transformations on this function. So I have f of x equals 2 times the absolute value of 3x minus 1 plus 4. So we're just literally going to go straight in order. Notice I have the 2 out front. So the 2 out front is an a value. So if I go over to the cheat sheet that you should have, if I go over there and I look, okay, so it says if a is negative, it reflects over the x-axis. Well, this isn't a negative 2, so I don't have that case. If the absolute value of a is bigger than 1, then it's a stretch by a factor of 1 over a. So I'm going to say, what's the absolute value of 2? Well, the absolute value of 2 is 2, and 2 is bigger than 1. So this tells me that my graph has a vertical stretch by a factor of a. So I'm going to say vertical stretch by the factor of a is 2. So I'm going to say vertical stretch by 2. So that's the first transformation. Then I'm going to move inside my absolute value bars. So for the next one, it's my b value. So notice I have a value in front of x. It's a 3. So the 3, this tells me I'm going to look at what does b do to my graph. So that's looking right here. So if b is negative, it reflects over the y-axis. Well, this is a positive 3. So I'm not in this case. If the absolute value of b is greater than 1, then I have a horizontal compression by a factor of 1 over b. So let's see. I have absolute value of 3 equals, so the absolute value of 3 is 3, and that is definitely bigger than 1. So this means I'm going to have a horizontal compression horizontal compression by a factor of And it's going to be the reciprocal of 3. So the reciprocal of 3 is 1 over 3. So let me move down just a little bit. So far I've had 2 transformations in this function. I've had the 2 out front. Now I have the 3 inside. Now I have the -1 inside. So the -1 inside. So if we just follow this template that we have, well, the -1, that's an h value because it's being subtracted from our x value. So if we follow it down, so here's my h. If h is positive, then we move left. If h is negative, then we move right. So in this case, h is negative. So it's going to move our graph right by 1 unit. So it's 1 unit right. And then the +4, this is going to move your graph. If I look at what the k does, k moves your graph. This will move your graph up 4 units because it's positive. So when you do transformations, you're just going to follow what your template says to do. So you're going to just identify A, B, H, and K. So you need to identify each of those. Sometimes you won't have a B value, and that's okay. You just won't have a B value. So you won't have a horizontal stretch or compression. But you will likely have either a vertical stretch, a shift left and right, or a shift up and down. Those 3 we'll see a lot with absolute values. The parent function of the absolute value functions is f of x equals absolute value of x. The vertex, so the vertex will identify after we graph the function. So here, the parent function f of x equals absolute value of x. We're just going to make a table. So x, y. And I'm going to pick 0, -1, and 1. I'm just going to pick those 3 values. So if x is -1, my y is 1, because the absolute value of -1 is 1. If x is 0, then y is 0, because absolute value of 0 is 0. And if x is 1, then y is also 1, because the absolute value of 1 is 1. So I'm going to plot these 3 points. I'm going to plot 0, 0, 1, 1, and -1, -1. So I'm just going to plot these points. So this is what my graph looks like. There is no transformation taking place. This is the parent function. The vertex of the parent function is the highest point or the lowest point on the graph. In this case, this vertex here is the lowest point. There's no point. We don't ever use anything below the vertex. We never use any of this. So the vertex is the ordered pair. This is the ordered pair 0, 0. So the vertex here is 0, 0, and I know this is the vertex because there's no point below this point. So it's the minimum. The parent function of the absolute value function has a domain of all real numbers. So we can use the whole x-axis. It's always going to be -infinity to infinity for all absolute value functions. The range, if we look at the graph and we sort of use the vertex as a starting point, notice the y value here is 0. And all my other y values, I don't use anything below 0, but I use everything above 0. So I use all the y-axis. So remember, all of the y-axis above 0 would be like +infinity. So the range goes from 0 to infinity. And then for end behavior, as x approaches infinity, y approaches blank. And as x approaches infinity, negative infinity, y approaches blank. So again, if you'll recall, when we're looking at the end behavior, we're just looking at what is the left and right arrow doing. So for the first part, as x approaches infinity, since that's in positive infinity, we're going to be looking at the right arrow. Notice the right arrow is pointing up. Remember, the way we say up is +infinity. So here we're going to write infinity. And then as x approaches negative infinity, what value does y approach? So remember, negative infinity is like saying when we're looking at the left arrow. So when x approaches negative infinity, we're looking at the left arrow. Notice the left arrow is also pointing up. So that's also plus infinity. So this is the end behavior for the parent function. So let's look at an example where we have a transformation. So here's example 1. I have f of x equals the absolute value of x plus 1. So let's go ahead and graph the transformation first. So I'm just going to plot my parent function. So I'm going to plot 0, 0, 1, 1, and negative 1, 1. So this was the parent function. I did the parent function in blue. The transformation, so now notice there's no a value. I just have f of x equals absolute value of x plus 1. There's no a value. There's no b value because there's no value with the x. But there is a value inside here. There's this plus 1. The plus 1 is an h value. And then there's no k value. So remember, h does the opposite of what's there, so it's going to move my graph 1 unit left. So this is a transformation, and I'm just going to apply this transformation to my blue graph. So I'm just going to take all these 3 points and move them to the left by 1. So move this one left, move this one left, and move that one left. So all I did, just move each of those points left 1. So this is my new graph. Let's go ahead and answer what is the vertex. So remember, the lowest point on the graph, and this time we're looking at the green graph, not the blue graph. So the lowest point on the green graph is this point right here. So this point has the ordered pair -1, 0. So this is my vertex. It's -1, 0, because it's the lowest point. I never use anything down in this region down here. None of this part of my graph gets used. Only what's above the vertex. So the domain, remember, this is absolute value, so the domain is going to be -infinity to infinity. The range, this one's going to be similar to our parent function. So I'm going to start at the vertex. So remember, range is dealing with y, so here's 0. All my other y values are going to be above 0 because my graph goes above the vertex. All my other y values are above 0. So this is all the way up to plus infinity. So my range is going to start at 0 and go all the way up to infinity. And then for end behavior, as x approaches infinity, y approaches blank. And as x approaches negative infinity, y approaches blank. So you remember, you're just looking at, for the first one, you're looking at the right end of your graph. So the green graph, the right arrow goes up. So that means as x approaches infinity, y approaches infinity. For the second one, as x approaches negative infinity, remember you're looking at the left arrow. The left arrow is also pointing up. So we say as x approaches negative infinity, y approaches infinity. So this is the end behavior for that one. So we're going to do one more example. So example 2. I have f of x equals 1/3 x plus 2. So let's go ahead and describe the transformations and then we'll graph this one. So you're going to identify, if we go straight in order, 1/3 is in front of the absolute value. So this is an a value. So 1/3 is an a value. I don't have anything inside the absolute value with the x. And then I have this 2 outside. So this 2 here is a k value because it's outside the absolute value and it's being added. So these are my 2 transformations. So remember, what we want to look at the absolute value of a. So if the absolute value of a, so a is 1/3. So this is the absolute value of 1/3. It's 1/3. This is in between 0 and 1. So this means I'm going to have a vertical compression by a factor of 1/3. Then my K, remember K moves your graph up or down. Since it's positive, it's going to move it vertically 2 units up. To graph this one, we're gonna make a table. So I'll write the table right here. And then the values that we're going to pick for x, just so that we get whole numbers, I'll help you. The values that we're going to want to pick are -3, 0, and 3. So the reason why I'm picking these ones is that it's going to give me a whole number when I plug in to find my y. So when I plug in -3, notice the absolute value of -3 is going to be 3. And if I multiply 3 by 1/3, I get 1. And then I'm going to add 2 to it. So it's going to be 3. If I plug in 0, I'm going to get 2. If I plug in 3, I'll get 3. So these are my y values. So I'm going to plot these ordered pairs, 0, 2, -3, 3, and 3, 3. And then connect them. So this is my transformation. The last thing before we do domain, range, and end behavior, we need to look at the vertex. So remember, the vertex is the highest or the lowest point. In this case, the vertex is the lowest point because there's no other point smaller than this point. This point is the ordered pair 0, 2. There's no other point below this. Everything else is above this. Even though the graph spreads out quite a bit, this is still my vertex. All those x values, they don't grow nearly as fast, but they are growing, and they are all bigger than 0, 2. So all the other points in my graph are bigger than this point. The vertex is 0, 2. The last piece, domain and range. So domain, again, this is the absolute value, so it's going to be -infinity to infinity. Range, again, we're looking at the lowest point. So the lowest point here is 0, 2. So that means I'm going to start on my y-axis at 2, and then all my other y values go up from there. So 2, 3, 4, all the way up to positive infinity. So my range this time, it goes from 2 all the way to infinity. And then for end behavior, as x approaches infinity, y approaches blank. So we're looking at the right arrow for that one. So notice the right arrow points up. So as x approaches infinity, y approaches infinity. And then as x approaches -infinity, y approaches, so if we look at the left arrow this time, y is going to approach positive infinity because that arrow also goes up. So as x approaches -infinity, y approaches infinity. So this does it for the notes on absolute value transformations. We will do some more practice with this during our live meets.